the coordinate systems and transformation. Now, why do I need to do coordinates and transformation? Basically, any object or anything that I would like to visualize, I need to superpose, project the data on a specific model or a specific surface or a specific diagram. Now, most of us have a visualization surface which is a two-dimensional surface. In future, it need not be a two-dimensional surface, as in the video you have seen, it visualizes on buildings, on different surfaces which is available. So you may have screens which may be spherical in shape, or depending on the situation, you may have specific way of visualizing the data. But most of the visualization that we see, the television which has been working out, and they have been visualizing on a two-dimensional platform. It can be they visualize a three-dimensional graph on the floor of the studio. As you must have seen, sometimes they have something called the magic board. They show it on a screen, or they sort of they walk across on the graph, and basically they're walking on a green VR system, and using computer graphics you generate the visualization around the newsreader as if the newsreader is involved in the analysis of the data, or is within the data of the process. So all this, to visualize it, you have a three-dimensional data, you need to transform it or you need to project it on two-dimension. Depending on this will require some mathematical tools, and these mathematical tools come as coordinates and transformations. So we need to actually go into coordinates and transformations. Now, I would advertise now here, if you all of you do a Google a YouTube search for Pavan Chakravarti graphics and visual computing. So there is a sequential videos which I had created for the last semester. This is a BTech course. So basically it deals with some coordinates and transformations which is there. So I would urge you to maybe go through these videos to get a picture. But now the same, I will use the similar slides to explain data visualization in the explain the projections and transformations in the context of data visualization. There it was basically visualization or using it to generate graphics. Again, here I'm again generating graphics, but this graphics is essential to basically data representation which is there. So we will talk about coordinates transformation. So to begin with the definitions, you have a point. It's a location in space, 2D or 3D space. A point in geometry is a location. It has no size, no width, no length, no depth. A point is shown by a dot. Now, here I've said sometimes denoted by 1 pixel. Now, it is not possible in a digital display mechanism to have an infinitely small dot. What you have is a finite size dot, which you call it a pixel. 1 pixel is the basic image element of your screen, or it contains just one data point, or you can represent that is the pixel which is there. Now, a line segment, a straight path connecting 2 points. This is important that it is basically a straight path connecting 2 points. What is it? It is again made out of these points. It is infinitesimal width, consistent density, begins and ends with a point. So this is important. It is consistent density and uniform width. Now please note here, when you have already pixelized screen, the pixelize of the screen, the pixels are rectangular in shape, and when you place the rectangles one beside the other to form the line, it certainly will not be of uniform width, or it will not be an infinitesimal width. Okay, it will have a finite width, and this finite width will vary in thickness. And to understand that, you need to this is basically the problem of sampling. Anything you sample creates a distortion, and you lose on the higher frequency term, the smoothness of the term. And this is the artifact of sampling of data. And because of this, you will have this effect. So to clear this effect, there is something called anti-aliasing and other things in graphics, which you might have studied. I will not take it up as part of this lecture, but then I have a YouTube video on anti-aliasing. If you go through my course on graphics and visual computing, you will certainly get a video on anti-aliasing here. So here I've called this a line which is there. Why the line will be important? Because when we try to fit data and try to show some relationship data, we will learn how to do a least square fit. So least square fit will be, LSQ will be a fitting of the data using a straight line. And then we will also see how to fit a curved surface or a curved figure, and how sometimes the curve, if it is an exponential curve, you can actually represent it as a logarithmic graph. And by doing a logarithmic graph, you can linearize the curve, and by linearizing, it sort of simplifies you for fitting and other purposes. It makes it much easier to perform. Right. Now, now definitions in graphics definition, the point is known as a vertex. Okay, it's a point in 3D. Edge is a line. It could be an edge of a polygon or a surface. So 3D connecting two vertices is called an edge. Polygon, face, facet, or surface, they are one and the same thing. Basically, I will call that surfaces. I could have multiple surfaces. Of course, I'm showing these surfaces on a two-dimensional screen. So what you see is a projection of these surfaces onto a screen. I will come to this visualization at a little later stage when I develop my transformation. So arbitrary shape formed by connected vertices, fundamental units of 3D computer graphics. Right. So here what you see here is a point. Here it's shown as a sphere where it is varying, some x, y, z is varying, and you can show it in a coordinate system which is in this way, and these vectors x, y, z is perpendicular to each other. So this is called a Cartesian coordinate system in 3D. In 2D, as it is shown up here, the figure can be shown here where I've got a point which will change in the surface. Assume that the z component doesn't exist, so you can only take the top surface of the thing. So it becomes a two-dimensional problem. But what you see here is a three-dimensional problem which is visualized over a screen which is two-dimensional. The screen, or your computer screen, or your mobile screen through which you're displaying my presentation or listening to me shows you that this is a projection. It is a projection, and it may be an orthographic projection. We'll come to different types of projection. One is an orthographic projection and another is a perspective projection. We will deal with this later. So basically it tells you it is a sort of a connection of orthonormal planes, an x plane, xz plane. I can't say x plane, x is a single vector. Xz plane, xy plane, and zy plane. Okay, zy plane, x plane, and y. These are the different planes that you have in the process. So these are called Cartesian coordinates in 2D and x, y, z in 3D. Now I come to the next coordinate system. This is a little different, is that sometimes things happen on a cylindrical manner over a surface of a cylinder. There can be multiple examples. Assume that, for instance, I would like to show you the example of Parliament with time, z-axis being time, and I would like to show the strength of parliamentarians in the Parliament as the sessions are there, and whether sessions are not there over the years. Say when say previously when the Congress was in power, when then you had Atal Bihari Vajpayee's government, again Manmohan Singh's government, now you have Modi's government, so BJP's government. So you can show the trend of how the attendance of the parliament using a semicircular and the z-axis with the time. You could try to show with time how the things kept varying. No, semicircular or a full circle, it would use a coordinate system, and for which you need to convert. So what you have is the coordinates which are there. One is the z-axis, the other is the r-axis. This is r cylindrical, which is perpendicular to z. Okay, which is on the xy plane, and you have the z-axis. So what you have is, since r is perpendicular to z and which is on the xy plane, so you can represent r as r cos phi and r sin phi. Now phi being the other angle on the xy plane, basically starting from x moving over towards y, showing you the direction of r. So this forms the cylindrical coordinate system, which is r phi z. So r phi z is the cylindrical coordinates which is there, right? So, and the conversion from a cylindrical coordinate to a Cartesian coordinate, because Cartesian coordinates are one of the best understood, or a rectangular coordinate system. So you can find out x as a function of r cos phi and y as r sin phi and z as equal to z. Z doesn't change. So please note here the figure here, this r, okay, this is different. The red color is not the radius r. R is this. R is on the xy plane. This is z, and the angle at which this point is at an angle phi. So you can explain the space over in this manner, which is there, right? So here I've got, say, I would like to show in which direction things are on the surface, this horizon. I could do it through this. So here you have unfortunately it is not showing me the relationship here. Next I come to the coordinate systems. This is a spherical coordinate system. Spherical coordinates are basically similar to the coordinates of longitude and latitude, or the GPS coordinates that you get, because r you're not bothered, because GPS coordinate also gives you r, that is gives you altitude. It you only make use of it only when you're climbing mountains or anything, or otherwise normally it would be useless. You only generally are bothered about the longitude and latitude of the object. So basically this shows you the relationship. And now please see, the R is no more in the XY plane, but it has a direction which is there. So here Z, it makes an angle theta with Z. So if it makes an angle theta with Z, the Z component is equal to R cos theta. So the projection of R, the direction R on the XY plane is R sin theta. Since this is R cos theta, this is the projection is R sin theta, and the X is cos phi and Y is sin phi. So can you prove from this? This is another problem, is that if I would like to convert these coordinates to if I would like to convert these coordinates to what you say, the cylindrical coordinate system, what should be the value of theta? Please note here. So what should be the value of theta? Okay, theta is the angle from the z axis. Okay, so in this case it will show you some value, and obviously the z component will become 0. So then you can add to this z a threshold or an offset, which you can call it plus z naught. Okay, plus z naught to give you an offset, and this z naught. So you will see that this will become 0, this will become 1, this will become 1, and will reduce it back to r cos phi, r sin phi, right? And z will be equal to z naught, which is there, right? So this is called spherical coordinates or polar coordinates, and sometimes called equatorial coordinates when compared with the Earth. It is called the equatorial coordinate system, and that is generally used by astronomers. For us, spherical coordinates or polar coordinates are sufficient. And what you see is that to locate yourself on the globe, you use this coordinate system, and you have with this, which is the GPS, which allows you to navigate on the Earth for different longitude and latitude. So here you see a particular latitude which has been marked in red, which is maybe close, which is above the Tropic of Cancer. So it tells you a location of the latitude of the Earth. So here is a global positioning GPS system on your mobile, which gives you the longitude and latitude. And for visualization, you place yourself on the map of the Earth, and the Google Maps shows your location on the Earth and tells you where you're standing. And then you can also visualize, say, if I want to move from A to B, if I know the longitude and latitude of B, it tells you the graph or the connected path through which I can move from A to B. Please note, when Google actually shows you the path, it doesn't tell you how the crow flies. It tries to navigate you through the shortest path to this location. You can vary this path using dynamic method, but then the problem becomes it's a traveling salesman problem, and it becomes an NP hard problem of visualization again. So please note that sometimes you don't have a road, and maybe on the map the road is there, and Google has not taken cognizance of of the thing, you will see that it will sometimes direct you towards a region where you will suddenly find a wall facing you. But as per Google, that actually wall does not exist, and there is a path through that region. So you may make mistake and take up different paths, seeing Google Travel or Google Maps to travel through the space. Now, how does GPS work? What it does is that it has multiple such satellites which is rotating the Earth, and by these satellites, your position is triangulated. Basically, you're getting your signal from these three different objects. You can actually position the person at different locations. So in this case, it has positioned itself in North Africa, somewhere near Sudan or somewhere, where the GPS has cornered or centered the person here. So here you have here which shows you that at a particular time, this visualization tells you the number of satellites which the object actually verifies, and it tells you that, see, 3 points will give you a triangulation, but every triangulation will have an error. Now, if I can get these 3 by 3 points by using multiple satellites, say for instance, if I've got 4 satellites, I can sort of pick up, I guess, 2 different types of triangle. Two different types of triangle, or more than 2 different types of triangle. I think 5 different types of triangle can be picked up to improve the signal to noise or improve the errors, the triangulation error, and to pinpoint a person in this manner. Right. So what you have is the 3-dimensional coordinates is the longitude, latitude, plus the radius, which will form the spherical coordinate of the Earth. So here you have the radius. Right. Now you have got common coordinate system. One, I call it the object space or local to each object. Now, if the object is spherical, then you use a spherical coordinate system. If the object is a cylindrical, you use a cylindrical coordinate system. If the object using a room which is rectangular in shape and other things, so you use the Cartesian coordinate system. So here is the object space. You can describe most natural coordinate system for a geometric object. So here is object frame. Then there is a world frame. If I would like to compare multiple objects and place these objects into one frame of reference, I can call it the world frame, which generally is a Cartesian coordinate system which may connect multiple such objects into its frame, common frame. So there are ways, or there are transformations where I can move one frame of reference into the other frame of reference using a series of transformations. So we will learn how to make these transformations. So what we do is that you move here from object to world space. Once you have moved to world space, right here. So here I've got the world space, and after you move into the world space, these are different objects. So here you see there is a bottle of sanitizer. There is a crank which which can make music, and there is a Rubik's cube which is there. So I have placed on my surface or on my domain, which is the surface of my laptop. Now, if this is my domain, I can define the object 1, 2, and 3, and I can determine the coordinate systems which is there. So it is using an Cartesian coordinate. So here you see the three vectors, the blue, red and green, describing the three Cartesian coordinates, and it shows you the coordinates of the Rubik's cube, the cube, with an orangish yellow coordinate, showing you the coordinate position of one of the points of the Rubik's cube. Okay, so this is again getting the distance to my second object, which is in blue, which is again is a bottle of sanitizer. Now this bottle of sanitizer is a cylindrical object, so describing this bottle in a cylindrical coordinate seems to be the best way, but obviously its position on the world coordinate will be Cartesian. Here what you see is a complex object which is made out of a crank, a cylinder and multiple such objects, which could be described as a complex object. Again, can be the object frame could be a mixture of multiple frames, but obviously its position on the world frame is determined by a Cartesian plane. Now we talked about the local object and the world frame, which is common to all objects. Now I come to the eye space or the camera space. Now the eye space or camera space will depend on how I'm looking at it. Am I looking it from the bottom? I'm looking it from the top? I'm looking it from the left side or right side? So basically I should be able to locate or place where my camera is, or from where am I locating the object. Right. So this location is called the viewing frustum or the eye space or the camera space. So it defines you the camera location of the object. Now what I mean the camera location is that from which direction am I looking at the data or the visualization that I would like to construct. So basically taking a projection in that particular direction. Now the projection could be orthographic or perspective depending on the situation that is demanded. So the next, when I generate these coordinate system, which is connected with the eye space or the screen space. So here you have got the thing moving from eye space to screen space, which is effectively, it's nothing but a projection of the eye space, which is a three-dimensional coordinate system which the head is going to get, and he is going to project it to a screen. Right. So here I have got the eye space or the camera space which has been defined here. So screen space which has been there. So here you again I move from object space. I move in by model matrix. I go into the world space. World space is viewing the matrix, and obviously I've got the camera space which is there, which again projects it to the screen space which is here. So let me try to see different types of transformation. Now what I call this is we use rectangle coordinate system called columns and okay, so I'll just come to this point. Now in graphics, how do I store the data? What is the data structure that I use? So I will have different tables. One table will be the vertex table. The other one will be the edge table. And the last will be the polygon surface table. Now, what is the difference? There is a hierarchy. As you see, this each of these table edges have been defined with a different color, which is shown here. So here first I have got the vertex table, which is having the coordinates of the vertices, the points. So I've got x1, y1, z1, x2, y2, z2, up to x5, y5, z5. So there are basically 5 different vertices here. Then I have the edge table. Edge table basically connects the edges of the table. So here you have got V1, V2, V2, V3, V3, V1, which actually generates a particular shape or a particular surface. So I've got 3 vertices. Obviously, when I got 3 non-aligned vertices, it forms a surface. So this defines the surface S1, which is shown in green. Similarly, if I show the screen, I have got the other 4 points, which has got 4 edges, E3, E4, E5, E6. You see that the edge E3 is common between the 2 surfaces, or it is the connecting edge which connects the 2 surfaces. It is possible that both the surfaces may not be on the same plane, but may be at different planes. Altogether, it depends on the vertices V1, V2, V3, and at the end stage, we just separate out the polygon surface table and then polygon volume table. So that was a representation, a graphical representation of the thing, showing you the different surfaces S1 and S2. Now the same thing that you represent in your computer, or how you would represent the points. So basically I will have a vertex linked list. So I will have a linked list of the points V1, V2, V3, V4, V5, which is shown here. Basically each link will contain the X, Y, Z coordinates, and it will connect a link to the other points which are there. Right, so I have this link of these points which is there, a linked list. Now this linked list, you connect it with another linked list of addresses, which you will call it the edge. So I have got 6 edges, so I will say that I've got E1, E2, E3, E4, E5 and E6, and each is connected using a connector or an address to different vertices. Like E1 is connected to V1 and V2. It also connects among itself, as if I would like to scan through the different edges. So it connects, E1 connects to E2, E2 connects to E3, E3 connects to E4, E4 to E5, and so on and so forth. So here it shows you the connection between the vertices and the edge. Similarly, I can have the connection between the edges and the surfaces. And what you see here, this was the green surface and this is the blue surface. So basically, when I have these different layers of thought process, or the way I have constructed my data structure for graphics, what I see is that the transformation has to be implemented on the vertices. Whatever transformation I use, linear, nonlinear, or any other transformation, I will implement it on the vertices and not on the edges, not on the 3-dimensional object keeping. So this is called a B representation linked list. So now let me go into the this was basically telling you how the vertices are stored, and now I come to the outline of my problem. So let me see, I have got another 10 minutes. Let me see. Let me just go through a little and maybe go up to classes of transformation. I'll take up the classes of transformation maybe in my next class. So let me just first define transformation to begin with. So I have transformation which is there here. So I have got my some value x which I would like to show it to you as a value x prime. And this I would say is a linear transformation. And the linear transformation is basically, I will say x prime is equal to ax multiplied by x plus bx multiplied by y, and y prime is equal to ay plus x, ayx plus byy. And obviously, in 2 dimension, I can add another term called translation. Both the origin of x and y and x prime and y prime need not be the same. The origin may be different, and to change the origin, I add translation, and this translation is defined as tx and ty. Now, the same thing in 3 dimension converts to in this manner, as you see here, the term which has come cx and cz, and the z which is shown here again, which is different. Right, so please see here the black is in 2D and the additional term in brown is making it into 3D. So this portion is the translational terms which is defined here. Now as you see, this simple transformation this linear transformation can be written in a matrix format. And the matrix format which shows you here in 2D again the same equation, as you see, it shows you as a matrix multiplication, a 2-dimensional matrix multiplication, which is the attribute ax, bx, ay, by, and you have the translational vector tx, ty, which is given here. The same thing, if I would like to describe it in 3 dimension, my matrix changes its shape and it becomes a 3-dimensional object, and you keep it in this way. Now please note here that I have got this translation which is an added term to the transformation. We will see them here. You will see that it's a vector which is giving you an addition to this. So it is possible after addition, it actually doesn't show, it shows you as a vector which is added. So later on we will see that how we can merge this vector into the transformation. So here is the Cartesian coordinates that we have described earlier, and you see the points as it keeps moving. Okay, so again, this is object space, world space, common. We have seen this eye space and screen space, which has been given. So here I have got just to give you an idea, I've come back to this diagram of my 3 objects placed over my laptop, so I can talk about a Cartesian space, or let me just talk about the Rubik's Cube in this case. So I've got the 3 coordinate systems, and then the Rubik's Cube can further be described by these 3 coordinate systems. I can sort of describe it by these vertices V1, V2, V3, V4, V5, V6, V7 and V8, which is there, which gives you the Rubik's Cube. Now if I remove the Rubik's Cube, I have the coordinates or the vertices of the cube which has been kept there. So you see that one of the vertices give you the object's coordinate. I've used that as the object's coordinate, which is marked in brown, and the edges of the cube is marked in green, and the vertices of the cube is marked by cyan. Okay, so okay, so here you see here is that this cube is not exactly aligned with my Cartesian coordinate system. It is disaligned by an angle theta. But in this case, I am actually not doing any calculations. So what you see here is the different vertices which is there, the 8 vertices, and 8 of these vertices describe the different edges that you have. I've taken some of the edges, the first and the last edge which is there. Right. So this is the object which is cube, and then I could have a similar thing for object 2, which is the bottle of sanitizer, or the crank, which is the object 3. Okay, so this gives you the table behind these objects. So we will see different simple combination, like say for instance, what is an identity transformation, what is translation, what is rotation, and isotropic transformation later on. And translation is basically moving the objects. Rotation we know. Okay, so I will stop here, and next time I will start from this translation or simple transformation which is there in my next lecture. So